Today we've got this nice infinite product to evaluate that I found in the Math magazine. So it's problem 1892 if you have access to this and you can check it out. So our goal is to calculate the limit as n goes to infinity of 1 over n to the n times the product as k goes from 1 to n of n times the square root of n plus n plus 1 times the square root of k over root n plus root k. And we're actually going to take a general approach, and that approach is to prove the following identity, from which our result will follow quickly. And that is if we take this limit as n goes to infinity of this, well, it's like an nth partial product of 1 plus 1 over n times f evaluated at k over n, we get e to the integral from 0 to 1 of f of x dx. And the motivation here is that this 1 over n f of k over n looks like what would be inside of a Riemann sum that is defining an integral. It's just, instead of being inside of a sum, it's inside of a product. But logarithms can change products to sums, so exponentials can change them back. That's why I've got this e to the integral. So that's the motivation here. That's not exactly how it plays out, but that is the motivation. Okay, so let's see how we might do this. So I'm going to start with introduction of some notation. So I'll let p sub n of f be equal to, well, this partial product before we've taken the limit. So we've got this product as k goes from 1 to n of 1 plus 1 over n f of k over n. Okay, nice. And now I'd like to notice the following inequality, which is fairly easy to prove. And that starts with the following equality. So if we take the natural log of Pn of f, that's going to be the same thing as the sum as k goes from 1 to n of the natural log of 1 plus 1 over n f of k over n. Because of that property of the logarithm that changes a product to a sum. Okay, but now, well, there's no inequality in sight yet, so we'd like to somehow build this into an inequality. And that'll go like this. So let's notice that 0 is less than or equal to x minus the natural log of x plus 1. So that inequality is fairly easy to prove. X is always larger than the natural log of x plus 1. But then the trick here is to express this difference as an integral. So notice that this is the integral from 1 up to x plus 1 of t minus 1 over t dt. So we could do that calculation if we wanted to, and it is fairly straightforward. So let's see maybe how that goes. Well, perhaps we would take that and we would write it as the integral from 1 to x plus 1 of 1 minus 1 over t dt, which that'll integrate out to t minus natural log of t evaluated from 1 to x plus 1. Okay, so now let's put something above this object. So in other words, extend this to a compound inequality. And we'll do that by deleting the denominator. But notice that by the bounds of integration here, the denominator is bigger than 1. So if we get rid of the denominator, we've created something larger. So here, this is going to be less than or equal to the integral from 1 to x plus 1 of t minus 1 dt. Okay, but then that, in fact, is equal to x squared over 2. And again, this one is fairly easy to calculate as well. So let's see. That's going to integrate out to t minus 1 quantity squared over 2. But then we need to evaluate that from 1 to x plus 1. So let's see. Evaluating that at x plus 1 will give us x plus 1 minus 1 squared. So that's x squared over 2. Evaluating that at 1, we'll get 1 minus 1, which is 0 squared. Okay, so that's cool. But now let's see if we can put this together into something that's a little bit useful for our circumstances. And in fact, we can if we take this inequality that we've developed. So I'll just focus on this bit that I'm underlining in magenta. So starting here, 0 is less than or equal to this x minus natural log of x plus 1, which in turn is less than or equal to x squared over 2. And we'll apply that with x replaced with this 1 over n times f evaluated at k over n. So let's see, that's going to turn our inequality into 0 is less than or equal to 1 over n times f evaluated at k over n minus the natural log of that plus 1. But observe that the natural log of that plus 1 is minus the natural log of that plus 1. So let's sneak that in there as well. So 1 plus 1 over n f evaluated at k over n. And then bound this above by that object squared. So we got 1 over n squared, f evaluated at k over n quantity squared. So that's where we're at the moment. We've got this nice inequality. Okay, so this is where we ended up on the last board. We have the following inequality. But let's observe that this portion of the inequality, the natural log of 1 plus 1 over n f of k over n, if we take its sum as k goes from 1 to n, we get this natural log of p sub n of f, which is an object related to, well, the infinite product. Well, it's not really an infinite product, the limit of a partial product that we would like to calculate. Okay, so that motivates us to take this inequality and then sum as k goes from 1 to n. So let's see where that leaves us. So we'll have 0 is less than or equal to the sum as k goes from 1 to n of 1 over n times f of k over n. And then from that we subtract, well, the sum of this, which that is simply the natural log of Pn of f. And then, well, I just observed that I missed a 2 down here. I think I missed it on the last board as well because we had an x squared over 2. So let's sneak that back in here. And then we'll sum that from 1 to n. So that's going to leave us with a 1 over 2n, and then the sum as k goes from 1 to n of 1 over n f of k over n squared. So notice I split those n's in the denominator inside and outside the sum. But let's look at this. This looks like an nth Riemann sum of some sort of integral. In fact, if we would to take n to infinity here, that looks like it'll give us the integral from 0 to 1 of f of x dx. I guess assuming that this is a Riemann integrable function, which we are implicitly assuming by writing this down over here. Okay, so that all in all motivates us to take the limit of this entire inequality as n approaches infinity. So that's going to leave us with a 0 is less than or equal to the integral from 0 up to 1 of f of x dx. And then minus this limit as n goes to infinity of natural log of Pnf is less than or equal to, so let's look at this. This other thing also looks like a Riemann sum. So let's put this yellow overline here and observe that now the function is f squared instead of f. So this should turn into the integral from 0 to 1 of f of x squared dx. But then we've got this extra factor of 1 over 2n out front. So I'll bring that in by just keeping the limit as n goes to infinity, intact. So that'll give us the integral from 0 to 1 of f of x squared dx. But that's multiplying into the limit as n goes to infinity of 1 over 2n. I, in fact, really split the limits up there, but that's okay because they both exist. But now let's observe that this limit as n goes to infinity of 1 over 2n is pretty clearly equal to 0, meaning that this whole side of the inequality approaches 0. But now we've bound this thing that's in the middle, this difference of the integral and that natural log object between 0 and 0, which means those two objects are the same. If we take their difference and get 0, well then they have to be the same. So let's write that down. So that means we have the limit as n goes to infinity of the natural log of Pnf is equal to the integral from 0 to 1 of f of x dx. But now exponentiating, we'll have the limit as n goes to infinity of Pn of f equals e to the integral from 0 to 1 of f of x dx. But given the way that we defined Pn of f, that's exactly what we needed for our lemma. So now let's see how that applies to our goal problem. Okay, so let's see how we can manipulate this product so that it looks like, well, the general product that we have over here. So first up, note that we can take all n copies of these n's into the product, and that'll just give us an n in the denominator. That's because we've got a product of n objects. So if you multiply n to itself n times, you clearly get n to the n. So that's the first thing that we're going to do. So we'll get rid of this and sneak it inside the product as an n in the denominator. And then we'll manipulate it a little bit. So this will give us the limit as n approaches infinity. We have our product as k goes from 1 to n of, I'm going to write this as 1 plus something because, well, I need to write it as 1 plus something. And then it turns into 1 over n times, so we've got radical k over n over 1 plus radical k over n. Great, so that's after a couple of steps of manipulation, but notice it makes it in this form right here. But the real question is, what is our function f? Well, just by visual inspection, we see that our function f here will pretty clearly be, let's see, the square root of x over the square root of x plus 1. So that means, well, our value here should be e to the integral from 0 to 1 of root x over root x plus 1 dx. So that means, well, we, in short, need to calculate that integral. So let's see how we might do that. Let's just bring it down here. We have the integral from 0 to 1, root x over root x plus 1 dx. Let's maybe set u equal to that denominator, root x plus 1. So let's see, that means that root x is u minus 1. That makes x u minus 1 squared. And that makes dx equal to 2 times u minus 1 du using the chain rule. So let's see. That's going to leave us with 2 times the integral of, let's see, we pick up a u minus 1 from the root x in the numerator, another one from the dx. That gives us u minus 1 quantity squared, or u squared minus 2u plus 1 over this root x plus 1, which is u du. And then what about our bounds of integration? Well, when x is 0, u is 1, and when x is 1, u is 2. So there we have it. But now let's maybe distribute this 2 through. We'll have the integral from 1 to 2 of 2u, and then let's see, minus 4 plus 2 times 1 over u du. So now we can take the antiderivative and plug some values in. So taking the antiderivative, we get u squared minus 4u plus 2 times the natural log of u evaluated from 1 to 2. But now from there, it's just some simple arithmetic, and what we'll end up with is the natural log of 4 minus 1. And that's because we can take this 2 and turn it into the natural log of u squared, giving us that natural log of 4. So let's see, that means our final answer will be e to the natural log of 4 minus 1, which we might as well write as e to the natural log of 4 times e to the minus 1, which turns into 4 over e after applying like standard rules. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.